a low metallic grinding, a deep vibration. Then darkness filled with dust. A single rotating cutter head, 600 tons of steel, inches forward through solid rock, 75 meters beneath the ocean floor. No windows, no GPS, no second chance.
Right now, we're standing above one of the busiest shipping lanes on Earth.
Cargo ships, tankers, ferries, thousands of them. But 75 meters below all of that, men once drilled blindly through solid rock, and when they finally met in the middle, they were off by less than half a meter. The rumble grows louder.
If they'd missed by just a few meters,
this entire project would have flooded. Cut to a vast CGI cross-section of the English Channel. Ships glide calmly above. Beneath them, a thin, pale band of chalk marl slicing through darker, unstable layers. This was the target, not the seabed, not the water. A 20-meter-thick layer of relatively watertight rock, suspended between porous stone above and clay that could seize machinery below. They had to hit it and stay inside it. For 39 kilometers, 2 nations, 11 tunnel-boring machines, 0 visibility. The year was 1988 when the real drilling began. But the obsession started nearly 2 centuries earlier. Napoleon dreamed of it. Victorian engineers attempted it with oil lamps and horses. Each time, the sea won, until Britain and France decided to stop dreaming and start drilling. On the English side, engineers faced a vertical wall of white chalk at Dover. To even begin, they blasted 250,000 cubic meters of cliff face, carving out an artificial plateau from raw geology. A new piece of Britain, manufactured by explosives. Across the water in Sangatte, France dug a 60-meter-deep circular shaft, a concrete cathedral beneath the earth. From here, their machines would descend and disappear toward England.
This is where it starts. He walks along a massive concrete shaft recreation,
running his hand across the curved wall.
Once the cutter head begins turning, there's no reversing. You commit, you go forward, for years.
Each tunnel boring machine, or a TBM, wasn't just a drill, it was a moving factory. The cutter head crushed rock. Conveyors removed debris. Hydraulic arms installed prefabricated concrete segments, each one forming a watertight ring. Those segments were the only barrier between workers and the ocean. On the British side, 6 machines launched, 3 toward the sea, 3 through land. The French deployed 5, including sealed-face excavators built to withstand wetter, looser ground conditions. Inside the tunnels, temperatures climbed to 50 degrees Celsius. Ventilation was limited. The air was thick with chalk dust. Imagine operating a 1,000-ton machine in a pressure cooker, miles from sunlight.
You're not just fighting rock down here. You're fighting heat, pressure, and time.
Time was merciless. Every day of delay meant millions in losses, but speed was dangerous. Drift a few meters too high, and they'd hit porous rock. Water would rush in, flooding the tunnel. Trapping crews. Drift too low, and clay could grip the cutter head, locking it in place like cement. They were threading a needle underwater. To stay aligned, engineers relied on a gyroscopic guidance system, an electronic compass immune to magnetic distortion. A laser beam projected the precise trajectory forward into darkness. The operator sat inside a control cabin, steering a 1,000-ton machine with the sensitivity of a surgeon. Millimeter adjustments, over kilometers. Cut to CGI, 2 glowing lines moving toward each other from opposite sides of the channel, the gap between them shrinking. But drilling creates spoil. And this project would generate 7.5 million cubic meters of it. On the British side, they made a bold decision: dump it into the sea. Over months, chalk debris accumulated into a 90-acre artificial platform. They didn't just dig a tunnel, they pushed the coastline outward.
When you don't know where to put 7.5 million cubic meters of rock, you build new land.
Meanwhile, the service tunnel, the smallest of the 3, advanced first. It was the Scout, the early warning system. Every meter was inspected for water seepage. Every leak immediately sealed with grout, because a sudden breach wouldn't just flood equipment, it could bury crews alive. Cut to darkness. A faint drip echoes. The tension wasn't just geological, it was geometric. After years of drilling, the British and French service tunnels were approaching each other, only meters apart, yet separated by 39 kilometers of blind excavation. No satellite correction, no external reference point, just math, gyroscopes, and trust.
Imagine standing underground, knowing that somewhere ahead of you, another team is drilling toward you. You can't hear them, you can't see them. You're betting everything that your calculations match theirs.
The final approach slowed. This wasn't brute force anymore, it was surgical. Engineers drilled a small pilot hole first, a narrow probe through solid rock to verify alignment. If the hole emerged wildly off target, it would mean years of error. Silence. Then, breakthrough. December 1st, 1990. The drill punched through, a small opening, a flicker of light from the other side, two worlds separated by sea, finally touching. The final alignment error, less than half a meter, after 39 kilometers, 75 meters underwater. That level of precision borders on impossible.
Less than the length of this arm.
He stretches his arm out inside the tunnel.
That's how close they came to missing each other completely.
But the story didn't end at breakthrough. The two larger rail tunnels followed, expanding the connection. And once complete, a question remained. What do you do with a machine too big to turn around? On the British side, the answer was simple. You bury it. 6 massive tunnel boring machines, each weighing nearly 1,000 tons, were sealed inside the earth beneath the channel. Abandoned, sacrificed, not because they failed, but because retrieving them would cost too much time. Steel giants entombed beneath the sea. The camera glides through the completed tunnel, smooth concrete rings curving into the distance, illuminated by precise bands of white light. What was once a claustrophobic excavation zone is now a controlled, engineered artery beneath the ocean. But carving the tunnels was only half the battle. Because once you create a 39-kilometer hollow space under the sea, you have to keep it alive.
A tunnel like this isn't just a hole in the ground. It's a living system. Air has to move, heat has to dissipate, electricity has to flow. And if something goes wrong down here, you don't get a second attempt.
Cut to CGI airflow simulation. Massive fans spin in slow motion. Blue streams of animated air surge through the tunnel network. Ventilation was critical. High-speed trains act like pistons, compressing air ahead of them. Without proper pressure management, shockwaves could build inside the tunnel, stressing infrastructure and affecting train stability. So engineers installed giant ventilation plants capable of cycling fresh air continuously. The entire tunnel atmosphere could be refreshed within minutes. Failure wasn't an option, because fire, not flooding, became the ultimate fear. Every 375 meters, cross passages connect the two main rail tunnels to the central service tunnel. The service tunnel isn't for passengers, it's a lifeline. A protected corridor designed for emergency evacuation and maintenance access. If a fire breaks out in one rail tunnel, passengers evacuate through reinforced doors into the service tunnel, once shielded from smoke and flames.
This third tunnel, Atla was the genius. It's why the system works.
He steps through a heavy steel emergency door, placing his hand against its thick frame.
Without it, a fire down here could turn catastrophic in minutes.
Power flows through 25,000-volt overhead lines, enough energy to move trains at up to 160 kilometers per hour underwater. The tracks are continuously welded for stability, engineered to absorb thermal expansion and vibration. But when you send a train through a confined tube at that speed, physics changes. Air pressure builds in front of the train like a moving wall. Behind it, turbulence. Engineers had to design pressure relief ducts and aerodynamic train profiles to prevent passenger discomfort and structural strain. This wasn't just a tunnel, it was a precision-controlled environment beneath the sea. Then came reality. In 1994, the Channel Tunnel officially opened. A political dream realized. Britain and France physically connected by steel and concrete. But celebration quickly collided with economics. The original projected cost? £4.7 billion. Final cost? Nearly double. The engineering was historic. The finances? Brutal.
Mega projects like this don't just test physics. They test politics, investors, public patience.
Cut to archival footage, construction cranes, workers in helmets, ribbon-cutting ceremonies. 11 workers lost their lives during construction. A sobering reminder that beneath every engineering miracle lies human risk. Yet the system endured. 2 years after opening, the nightmare scenario arrived. A truck shuttle caught fire inside the tunnel, fueled by tires and cargo. Thick smoke filled the rail tunnel. Temperatures spiked. This was the moment critics had warned about, but the design held. Fire suppression systems activated automatically. Ventilation redirected airflow to contain smoke. Passengers and crew evacuated through cross passages into the service tunnel. Every life was saved. The damage was severe, but contained.
This was the ultimate test. Not whether they could build it, but whether it would protect people when everything went wrong.
The three-tunnel design proved itself under worst-case conditions. Over time, operations refined. Safety systems upgraded. High Speed 1, the dedicated rail line linking London to the tunnel, reduced travel time dramatically. London to Paris in just over 2 hours. Faster than flying once you factor in airports, security lines, delays, underwater. Seamless. The camera follows a modern Eurostar train racing through the tunnel. Headlights piercing the darkness, wheels humming along welded rails. Above, ships continue their silent passage across the channel, unaware of the steel artery below.
For centuries, the English Channel was a barrier. Weather, water, war, separation. Now it's a crossing. 40 minutes from coast to coast. No waves, no ferries, just precision engineering beneath your feet.
But perhaps the most remarkable part isn't the length or the depth. It's the margin of error, less than half a meter after drilling blindly for 39 kilometers. In a geological layer only 20 meters thick, under constant pressure from millions of tons of water above. That level of coordination required synchronized surveying, redundant measurement systems, and relentless recalibration. Engineers constantly verified position using gyroscopes, laser guidance, and fixed reference networks from both shores. Every calculation had to agree, because if one side drifted, even slightly, the meeting point would shift irreversibly. And there was no external correction once deep beneath the seabed.
They weren't just building toward each other. They were trusting each other.
Cut to CGI replay of the breakthrough moment. Dust clearing as light pierces through from the opposite side. Hands reaching through the opening. The handshake wasn't symbolic. It was proof that human calculation could conquer geography. Today, millions of passengers and vehicles pass through annually. Freight moves between economies without interruption. The Channel Tunnel has become invisible infrastructure, unnoticed by most who use it. But beneath the calm surface of the sea, 6 British tunnel boring machines remain entombed, silent, permanent. Monuments to a decision made under pressure. Sacrifices for speed.
Those machines are still down there, buried, because turning them around would have taken too long. That's the scale of commitment this project demanded.
The Channel Tunnel stands as one of the most ambitious collaborative engineering feats in modern history, a structure not built above water, but beneath it, not visible from satellites, but critical to 2 nations. They drilled blind under the ocean, and when they finally met, they missed by inches. The rumble of a distant train echoes one last time beneath the sea.
Don't miss what's coming next. Subscribe and stay informed.